Yes, good morning, students. Here in this class, we are going to learn about the important concept, that is structure and bonding models. So let us move on to the today's concept. So the main important contents in our unit 1, structure and bonding models. Number 1, molecular orbital theory. The molecular orbital diagrams of homonuclear diatomic molecules and heteronuclear diatomic molecules. The pi-molecular orbital diagrams of benzene and butadiene. And the last concepts are calculation of bond order, and then crystal field theory, crystal field splitting in octahedral complexes. So let us move on to the first topic, molecular orbital theory. Coming to the molecular orbital theory, molecular orbital theory is also known as a very important theory for describing the molecular orbitals which are formed from atomic orbitals. By the combining of these atomic orbitals, molecular orbitals are going to be formed. So here it is developed by Robert S. Mulliken in 1932, and here the bonding is taking place between the atomic orbitals. So it provides answers to more complex questions, and it makes us to understand about the distribution of electrons, and in turn it can help to predict the molecular properties such as shape, magnetism and bond order. The main three important aspects of molecular orbital theory are: number 1, bond formation; number 2, reactivities or chemical reactivities; and number 3, magnetic property. Let us move on to the postulates of molecular orbital theory. So we know very well that here when two atomic orbitals of relatively same energy and orientation which can combine to form molecular orbitals, and according to the molecular orbital theory, how many number of atomic orbitals that are combined, that many number of new molecular orbitals are going to be formed. And you take the molecular orbital, it is a polycentric region. The electrons are revolving around many number of nuclei, that means 2 or more number of nuclei. That's why it is called polycentric nuclei. And the maximum capacity of a molecular orbital is 2, and the electrons are distributed or accommodated in molecular orbital with opposite spins. And let us have the very important so-called how these molecular orbitals are formed. So they are formed from a very important principle called linear combination of atomic orbitals, that is LCAO principle. So in case if the two atomic orbitals that are combined, so which have the same energy or very near energy and approximately have the same orientation, so then they will combine and forms new molecular orbitals. You see in the diagram we have 1s is combining with another 1s and gives rise to the formation of molecular orbital. And you take this, the formation of two kinds of orbitals. One is called bonding molecular orbital formation in the first step, and the second representation is related to anti-bonding molecular orbital, and we will learn about these bonding and anti-bonding terms in the next coming postulates. And you see the next important point is that here, let us see here, each molecular orbital is given by a wave function psi, and it is known as molecular orbital wave function. And we already familiar that psi square, it is representing the probability of finding an electron or probability density, and each wave function is associated with a set of quantum numbers which determines the energy and shape of the orbitals. And each wave function xi is associated with certain amount of energy, and the total amount of energy is sum of energies of occupied molecular orbitals, and the number of molecular orbitals formed is always equals to the number of atomic orbitals combined. And in order to distribute or fill the electrons in molecular orbitals, so we must follow some principles, and they are Hund's rule of maximum multiplicity, Pauli's exclusion principle, and Aubau's rule. And coming to the linear combination of atomic orbitals, how they are combined, the mentioned conditions are: in order to form a molecular orbital, atomic orbital should possess same energy and should possess same energy, symmetry, should possess the same energy actually, and relatively same orientation. Okay, and of course here, so we will have the next important aspect: what is a bonding molecular orbital and what is the anti-bonding molecular orbital. While we are learning about the bonding molecular orbital, you see here, you see the s orbital is combining with another s orbital and gives rise to a molecular orbital, and here 1s atomic orbital is combining with 1s atomic orbital, 2s atomic orbital is combining with 2s atomic orbital, and 2s atomic orbital can even combine with 2p x orbital, and as well as 2p y orbital is combining with 2p y, it will combines, and 2p z orbital can combine with 2p z atomic orbital. But you take this so called, the next important aspect is there is no molecular orbital that is going to be formed by the combining of atomic orbitals of 2s and 2py or 2pz, because we have the different orientations. One is the 2s orbital is having the orientation is different, and the symmetry is different from 2py and 2pz orbitals. Okay, that's why 2s orbital can combine with 2px but not with 2py or 2pz orbital atomic orbitals. Okay, now you take in the case of a combination of p orbitals, we have a px combination is there, py combination is there, and pz combination is there. Okay, now coming to the atomic orbitals, we have learned, and we have learned about the molecular orbitals, and you see this is the wave function analogy, how their atomic orbital waves, that means psi, which generates molecular orbital formation. So we have how molecular orbitals undergoing two kinds of destructive and constructive type of interaction. You see, in this case, molecular orbitals, so while they are going to be formed, so because of the combination of atomic orbitals, so when atomic orbitals of the same sign, same wave function that are combined, or else if the atomic orbitals undergoing constructive type of interaction with its wave function, then it is going to give a molecular orbital formation, and that kind of molecular orbital formed is called bonding molecular orbital. And the formed bonding molecular orbital is represented with we have psi a b is equals to psi a plus psi b. This is a bonding molecular orbital. And you see, in the case of bonding molecular orbitals, so there will be a constructive type of wave. In the first diagram, you will see there is a constructive wave. That's a bonding characteristic property, which is represented as xi. Whereas the very important point is that the atomic orbitals that are combined for the formation of the bonding molecular orbital, the resulting bonding molecular orbital has lower energy than the combined atomic orbitals. That's why the bonding molecular orbital will be placed below the combined atomic orbitals energy level. So they will go to lower energy state. So that will be shown in the diagram. You see, py is a atomic orbital, while you take the py bonding molecular orbital, which is present, which is less in energy when compared to the atomic orbitals that are combined. And going to the antibonding molecular orbital, the antibonding molecular orbital, which is going to be formed by the combining of atomic orbitals with their opposite signs or opposite wave functions, and resulting in formation of a new molecular orbital that is called antibonding molecular orbital through the destructive or subtraction process. So through subtraction process, the antibonding molecular orbital is going to be formed. Okay, and it is the antibonding molecular orbital. This antibonding molecular orbital formed is with highest energy than the combined atomic orbitals energy. Therefore, antibonding molecular orbital will be placed above the combining atomic orbitals. So you can see it in the picture. So there is a bonding molecular orbital which is present down, whereas the antibonding molecular present is at the top. And this is a representation of one bonding molecular orbital and antibonding molecular orbital by the combining of atomic orbitals py and py. And this is the wave kind of representation of bonding molecular orbitals and antibonding molecular orbitals with nodal planes and nodes. So it is a constructive interaction. This is a destructive interaction. Constructive interaction is also called as addition process, whereas destructive interaction is also called as subtraction process. And coming to the characteristics of bonding molecular orbitals, there are some very important characteristic properties. The difference in energy present between combining atomic orbital and the formed bonding molecular orbital is called as stabilization energy. And if the number of atomic orbitals, the number of the atomic orbitals which are combined to give bonding molecular orbital formation are high, means then the stabilization energy is also high. So what is the important point here? Here the number of bonding molecular orbitals is more, stability is also more. While we go to the antibonding molecular orbital on the other side, so here the antibonding molecular orbitals are formed by the subtraction process. Here the energy difference present between combining atomic orbitals and the formed antibonding molecular orbital is called as destabilization energy. And here the number of antibonding molecular orbitals that are formed is more, means then the stability is less. So here you see, in the case of bonding molecular orbital, now we will see some important points. Number one, bonding molecular orbital undergoes attractive forces. There is electron density is more, therefore more attractive forces are present in the bonding molecular state. And the next point is that the atomic orbitals of same sign that can combine to give bonding molecular orbital formation. And the next third point is that it provides stability to the molecule, And coming to the next point under bonding molecular orbitals, the bonding molecular orbitals shows attractive interactions, or else they will undergo addition process and with a constructive interaction. So they will show constructive interaction or addition process and resulting in formation of the very important bonding molecular orbital. So these are the important characteristics of bonding molecular orbitals. So let us move on to the antibonding molecular orbitals. The antibonding molecular orbitals are having certain important characteristics. Number one, antibonding molecular orbitals provide d-stability to the molecule, and here they will undergo destruction or destructive or subtraction type of interaction. And the third one, the electron density in antibonding molecular orbitals is less. And next point is that the bonding molecular orbitals which are formed from the atomic orbitals have less energy and more stability, while the antibonding molecular orbitals that are formed from combining atomic orbitals of opposite signs have more energy and less stability, and their electron density is also less. And these are the some important characteristics of bonding and antibonding molecular orbitals. And you go to the point of xi square, which is a probability of finding an electron. The xi square is represented as probability density. Here the probability of finding an electron or probability density of bonding molecular orbital is always greater than that of probability density of antibonding molecular orbitals. So this is represented as xi square, and xi square and xi star. What is the xi means bonding molecular orbital, xi star means antibonding molecular orbital. Now the very important relation between xi and xi star is represented by xi square is equals to xi star square plus 4 psi a psi b. This is the formula. And you take the next important aspect of what is a non-bonding orbital. So you see that there are bonding molecular orbitals and there are anti-bonding molecular orbitals. And while we go for the non-bonding molecular orbitals, you see the non-bonding molecular orbitals are the orbitals which are inner orbitals, inner shell electrons, which are not participating in bonding. So you see that they are not going to be participating in bonding. So you see, so those are called inner orbitals. For example, you take this and in the complex, like for example we have if p orbitals are combining, if p orbital, that means second shell containing 2s and 2p orbitals are participating in bonding and anti-bonding molecular orbital formation. Therefore inner shell, that is 1s shell, becomes non-bonding. So therefore we call it as a non-bonding orbitals, molecular orbitals. The non-bonding molecular orbitals which are not considered for calculation of bond order. Okay, now we will have the next important point. What are the important symbols that are used to designate our bonding molecular orbitals and anti-bonding molecular orbitals? The bonding molecular orbitals are designated with sigma, pi, delta, epsilon, and so on, etc. And you see the anti-bonding molecular orbitals are designated with the symbols like sigma star, pi star, del star, epsilon star, and so on, etc. So these are the very important symbols of representation. So next we have the distribution of electrons. While distributing electrons in bonding and anti-bonding molecular orbitals, we will follow three important principles. We call them as Hund's rule of maximum multiplicity, Pauli's exclusion principle, and Auber's principle. Okay, so coming to the very important so-called Auber's rule, the distribution of electrons is based on the increasing order of energy. So this is based on 1s, 2s, 2p, 3s, 3p, 4s, 3d, that increasing order of energy. So the second is Pauli's exclusion principle. Here, according to Pauli's exclusion principle, there is a maximum of 2 electrons present in any orbital with a opposite spin. One is revolving and revolving and clockwise, other one is in anti-clockwise direction. And Hund's rule of maximum multiplicity will say that in case of orbitals with same energy, we call them as degenerate orbitals. So for example, dxy, dyz, dxz, dx square, y square, dz square. First, all these orbitals are filled with one electron each. Like example, like even p orbitals, you take px, py, pz. So each orbital, all three orbitals has to be filled with one each. After that, the pairing of the electron starts, and the fourth electron will go for pairing, and that is called Hund's rule of maximum multiplicity. Okay, so based on these principles, the distribution of electrons is taking place, and after distribution of electrons, we will find what type of magnetic property does the molecule possess. So you see that if the molecule consists of unpaired electrons on the top or valency shell, then it will exhibits paramagnetic behavior because of the presence of unpaired electrons. Okay, on the other side, if it contains a pair of electrons in all the orbitals like bonding and anti-bonding, then the molecule exhibits the very important diamagnetic property. So after this magnetic property, now we have some very important conditions for the molecular orbital formation. Let us look on to those conditions for molecular orbital formation. See, first one is atomic orbitals must be roughly of the same energy, and atomic orbitals with different energies or the wrong spatial orientations do not combine, and these are called non-bonding orbitals. And the orbitals must overlap one another as much as possible according to the rule of maximum overlap, and they should be close enough for effective overlapping. And in order to produce bonding and anti-bonding molecular orbitals, either the symmetry of two atomic orbitals must be the same, or else when they rotated about the internuclear line, both atomic orbitals must change symmetry in identical manner. And it is represented with the help of this example. You see, psi AB is equal to psi A, psi B, psi A plus psi B. This is bonding molecular orbital, and the probability of finding an electron or probability density is the psi square. Psi square AB is equal to psi A square plus psi B square plus 2 psi A psi B. Okay, this is about molecular orbital theory. And so after this molecular orbital theory, now we will be moving on to certain examples. So in order to solve this molecular orbital theory, so based on first important aspect is that we should be familiar with the very important molecular orbital theory. So we know very well. So up to here we have learned about what is the molecular orbital theory and what are the important salient features of molecular orbital theory. Let us move on to the molecular orbital diagrams of homonuclear diatomic molecules. So you see, the homonuclear diatomic molecules are the molecules with same elements that are combined or same atoms that are combined for the molecule formation. See, in the case of examples like H2, He2, Be2, B2, so Li2. So we have different molecules are there, starting with hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. All of them are elements. If they are combined with the same of the element or atom, so that will give rise to the formation of H2, He2, Li2, Be2, B2, C2, N2, O2, F2, Ne2. So these are the homonuclear diatomic molecules. And let us have the very important configuration order. So in order to fill the electrons, the energy levels are different for different molecules. From hydrogen to nitrogen, the molecular orbital configuration follows one specific order, and after nitrogen, that is from oxygen to neon, it will follow another order or specific another order. So this is the very important. Now let us see what is the order of energy level in the case of hydrogen to nitrogen molecules, that is molecules with 2 to 14 number of electrons. Now let us have nitrogen molecules, or from hydrogen to nitrogen, the energy level increasing order is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px is equals to pi 2py, sigma 2pz. So here actually, so next, pi star 2px is equals to pi star 2py and sigma star 2pz. So in this very important molecular energy level order, so the distribution of electrons takes place with the highest energy containing orbital is molecular orbital is sigma star 2pz, whereas pi 2px and pi 2py are called degenerate orbitals. And so let us have the nitrogen molecule. In the case of nitrogen molecule, there are two atoms that are participating in the formation of a molecule called nitrogen: atomic orbital of nitrogen and atomic orbitals of nitrogen. Let us have the distribution of electrons in nitrogen molecule. There are totally 14 electrons are present in nitrogen molecule. 7 plus 7 is equals to 14 electrons, because atomic number of nitrogen is equals to 7. Therefore totally 7 electrons are present in one nitrogen atom. Therefore 2 nitrogen atoms are present. Therefore totally 14 electrons are present. So now let us distribute the electrons in nitrogen molecule. While we take nitrogen molecule, the distribution of electrons takes place according to the configuration order: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p x2, pi 2p y2, and sigma 2p z2. There are totally 14 electrons that have been distributed. And if you look in the molecular orbital diagram or energy level diagram, in this energy level diagram of our nitrogen molecule, so the atomic orbitals are combining. So you see, 1s orbital of one nitrogen atom is combining with 1s atomic orbital of another nitrogen atom, and gives rise to the formation of two new molecular orbitals, that is sigma 1s and sigma star 1s. And in the next higher energy state, the 2s atomic orbital of another nitrogen atom combines with the 2s atomic orbital of nitrogen atom, so gives rise to the formation of two new molecular orbitals, sigma 2s and sigma star 2s. And the 2p orbitals, 2px, 2py, 2pz orbitals of one nitrogen atom are combined with 2px, 2py, 2pz orbitals of atomic orbitals of another nitrogen atom, combining to give totally 3 bonding molecular orbitals and 3 anti-bonding molecular orbitals. And you see, the lower energy bonding molecular orbitals are pi 2px, pi 2py, and sigma 2pz. On the other side, the anti-bonding molecular orbitals on the higher energy state, pi star 2px, pi star 2py, and sigma star 2pz. So this is the very important configuration of our so-called nitrogen molecule. You see, nitrogen consisting of, so what is the number of bonding molecular orbitals and number of anti-bonding molecular orbitals? Let us discuss on that. Here the sigma 1s and sigma star 1s are the non-bonding molecular orbitals or non-bonding orbitals. So you go to the 2s and 2p orbitals. Sigma 2s, sigma star 2s, pi 2px, pi 2py, sigma 2pz are the bonding and anti-bonding molecular orbitals. So among those orbitals, sigma 2s, pi 2px and pi 2py, as well as sigma 2pz also, these 4 molecular orbitals. So let us say once again, sigma 2s, pi 2px, pi 2py, and sigma 2pz molecular orbitals, which are called bonding molecular orbitals with pair of electrons. And the remaining are sigma star 2s orbital with, which is having a pair of electrons and it is anti-bonding molecular orbital, and therefore we have totally 4 bonding molecular orbitals with pair of electrons and 1 anti-bonding molecular orbital with a pair of electrons. So in order to calculate the bond order, we have a formula that is called bond order is equals to it is the half of the it is the half of the bonding molecular orbitals minus anti-bonding molecular orbitals. So it is to be taken, and now the bond order formula is equals to number of bonding molecular orbital electrons minus number of anti-bonding molecular orbital electrons divided by 2. This is the formula. So therefore you take this is the formula which is given by bond order is equals to NB minus NA divided by 2. So if you calculate the bond order, so the bonding orbital electrons are totally 8 electrons. So because sigma 2s, pi 2px, pi 2py, sigma 2pz, 4 molecular orbitals with pair of electrons, therefore 4 into 2, 8 electrons. Understand? These 8 electrons are called bonding molecular orbital electrons. Minus anti-bonding molecular orbital is only 1, that is sigma star 2s with 2 electrons, therefore 2 minus 2 divided by 2. 8 minus 2 divided by 2 becomes 6 by 2 and it will becomes 3. So the bond order is equals to 3 for nitrogen molecule, and here in the case of nitrogen molecule there is a triple bond that is present in a nitrogen molecule with a bond order of 3, and 2 pi bonds are present and 1 sigma bond is present, and it has a highest bond dissociation energy and very less or low so-called bond length. So here bond order is directly proportional to bond dissociation energy, and bond length is in inversely proportionality relationship. Okay, now you take the bond dissociation energy, it will be approximately around 945 kilojoules per mole of the energy is present for this nitrogen molecule with a triple bond. And we have seen that there is a very important aspect of 110 so-called, it's a very important so-called 110 value is given for bond length. So okay, so this is the bond length of nitrogen molecule. So least bond length, highest bond dissociation energy. And if we go for the next important aspect, that is called what is its magnetic property. So nitrogen molecule is having a pair of electrons that are present in higher valency state, because all molecular orbitals are completely filled with electrons, therefore it exhibits diamagnetic property or diamagnetic nature. So coming to nitrogen molecule, nitrogen has a bond order of 3 and it is having 2 pi bonds and 1 sigma bond, and it exhibits diamagnetic property, and therefore nitrogen molecule is having a electronic configuration where the energy level diagrams is explained with the help of this particular diagram. Okay, so hope you all understood. Next we'll go to the next molecule, that is called oxygen molecule. You see, oxygen molecule, from oxygen to neon, the electronic configuration order of molecular orbitals is going to be somewhat different from the previous case, because from oxygen to neon it will follow a different order. Let us have that very important oxygen molecule now. In case of oxygen molecule, so oxygen is with an atomic number of 8 and which has 8 number of electrons, and therefore totally 8 plus 8 totally 16 electrons are present. So the molecular orbital energy level diagram is given in this particular picture, but you see what is the electronic configuration order. So while we go for the electronic configuration order, it is given with sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px is equal to pi 2py, next pi star 2px is equal to pi star 2py, and sigma star 2pz. So this is the oxygen molecule configuration, and you see in this configuration order there is a shifting of the orbitals. Like previously we have observed nitrogen molecule is with pi 2px, pi 2py orbitals are with lower energy, and sigma 2pz orbital is with higher energy. So but in the case of oxygen molecule, sigma 2pz orbital is with a lower energy, comes down, whereas pi 2px and pi 2py orbital is with higher energy, goes to the top. And why it is happening like this? Because of the reason, in the case of oxygen and the coming next molecules like oxygen, fluorine, neon molecules, the very important so-called the difference between the two energy states is very less. The 2s orbital and 2px and 2py 2pz orbitals we have taken, the energy difference between this or these orbitals are very less. So therefore, while you take this energy difference is very less, the electrons that are distributed in 2s bonding molecular orbital and pi 2px and pi 2py bonding molecular orbitals will be very close enough, and they will exhibit electron repulsions. They will exhibit electron repulsions. Okay, so that's why pi 2px pi 2py orbital will go to higher energy state, whereas the 2pz orbital, because the z orbital is oriented along yeah, you see that in the case of 2pz orbital is having the lobe of this orbital, the lobes of these orbitals are present along z axis. So therefore the electron repulsions of sigma star 2s and whereas sigma 2pz orbital is very less. Therefore the electron repulsions of pi 2px and pi 2py, where the sigma star 2pz will be very high, and hence it will go to higher energy state, whereas the sigma 2pz will experience low repulsions with the sigma star 2s. So that's why the electron repulsions of pi 2px pi 2py orbitals which are orienting along x and y axis, they have more repulsions with the sigma star 2s, and at the same time sigma 2pz experience less repulsions because of the presence of z orbital, z orbital which is orienting along z axis, hence low repulsions. That's why 2pz orbital will go to lower energy state. So next 2px 2py will be moving on to higher energy state. So this is why the difference is there in the order, energy level order. So based on this order, so now we will have the next important one, that is a distribution of electrons in oxygen molecule. Therefore we know that there are totally 16 electrons are present in oxygen molecule. Let us distribute the electrons according to this specific order. So what is the order now? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, totally up to here 14 electrons completed. Now the remaining 2 electrons are present. They will be moving on to pi star 2px1 and pi star 2py1. So now let us see the diagrammatic representation. So if you look at this diagram, we will find there is a one side atomic orbitals of oxygen and other side atomic orbitals of another oxygen atom which are combining. So because of the combining of first 1s atomic orbital of oxygen and another 1s atomic orbital of oxygen, it will form sigma 1s and sigma star 1s. So both are filled with pair of electrons because at lower energy state, so there is availability of 4 electrons are present in their atomic orbitals. So it is becoming non-bonding orbital state, which is not participating in, which is not considered for bond order calculation. Now we will go to the bonding state and anti-bonding state of second shell, that is 2s and 2p. So you see in the diagram, 2s atomic orbital of one oxygen atom combining with 2s atomic orbital of another oxygen atom. Therefore it gives rise to the formation of sigma 2s and sigma star 2s, and the 4 electrons are distributed in these 2 molecular orbitals completely. And you see in the case of next higher state, 2p orbital of oxygen atom with 4 electrons, 2px2, 2py1, 2pz1, and on the other side of oxygen atom also have 2px2, 2py1, 2pz1. While they are combining, first there are totally 8 electrons that are present in the distribution of electrons under the 2p energy state. So therefore totally 8 electrons will be distributed as like first lowest energy, that is called sigma 2pz orbital with the 2 electrons with opposite spin. Next higher energy, that is the degenerate orbitals pi 2px and pi 2py with 4 electrons, that is pi 2px with 2 electrons, pi 2py with 2 electrons, and remaining 2 electrons will go and occupy pi star antibonding pi star 2px1 and pi star 2py1. So therefore this is the molecular orbital diagram of oxygen O2 molecule. Now let us move on to the what is this very important bonding molecular orbitals that are present in oxygen molecule. So there are totally sigma 2s, sigma 2pz, pi 2px, pi 2py, 4 bonding molecular orbitals are present, and sigma star 2s, pi star 2px, pi star 2py. These three are the antibonding molecular orbitals with electrons. So you take sigma 2s, sigma 2pz, pi 2px, pi 2py, or with pair of electrons in its molecular orbitals, bonding molecular orbitals. Hence the total number of bonding molecular orbital electrons is equal to 8. And you go to the next, sigma star 2s is a orbital, antibonding molecular orbital with a pair of electrons. And the next higher energy antibonding molecular orbital, so like pi star 2px and pi star 2py are with only one single electron each present in these two orbitals, these two antibonding molecular orbitals, and therefore totally 4 antibonding molecular orbital electrons present in oxygen molecule. Hence based on this, bonding molecular orbital electrons is equals to 8, and anti-bonding molecular orbital electrons is equals to 4. Let us have the very important so-called bond order calculation. Therefore bond order is equals to 8 minus 4 by 2, that is NB minus Na by 2, number of bonding molecular orbital electrons minus number of anti-bonding molecular orbital electrons divided by 2. Therefore it becomes 8 minus 4 divided by 2, and therefore it becomes 2. Okay, now this is equals to 2 again, because 8 minus 4 is equal to 4, 4 by 2 is equals to 2. Bond order is equals to 2 for the oxygen molecule. So oxygen has a double bond present in between the two oxygen atoms. So the double bond is with one sigma bond and one pi bond, and so here the very important molecular orbital is represented with a so-called around the bond dissociation energy value is going to be 498 kilojoules per mole, and its bond length is going to be 121 is its value of bond length. So that is the units, 121 value is going to be there for bond length units, and as well as for as far as bond dissociation energy is considered, it will be 498 kilojoules per mole of energy is present, and there is a double bond. And let us go further. What is its very important magnetic property? The very important magnetic property of this oxygen molecule is how to express it based on the unpaired electrons or pair of electrons. You see how many orbitals are present totally we have here in its valency shell. 1 2 3 4 5 6 7 and 8 orbitals are present. Among these, 7 orbitals are filled with electrons, and in that we have 5 orbitals are with completely with pair of electrons, whereas the remaining 2, that is pi star 2px, pi star 2py with unpaired electrons. Therefore the very important molecule is having unpaired electrons, therefore it exhibits paramagnetic property. Okay, it's clear, right? So now let us move on to the very important molecular orbital diagrams of heteronuclear diatomic molecules. Still now we have learned about what is molecular orbital and what are bonding molecular orbitals, what are anti-bonding molecular orbitals, and we have learned about different principles that are involved in the distribution of electrons and its magnetic property, as well as bonding in homonuclear diatomic molecules. Now let us move on to bonding in heteronuclear diatomic molecules. While we go for this bonding in heteronuclear diatomic molecules, so the heteronuclear diatomic molecules like CO and NO, and you take some other examples like Cn minus, all these three examples will makes us understand there are different atoms that are combining to give to give the molecular orbital formation. So here what is the very important aspect in heteronuclear diatomic molecules is that, so here carbon, for example, you take in the case of CO, C is a carbon which is combined with oxygen in its valence shell containing electrons. So therefore here in this CO formation, so how this CO molecule is going to be formed is, again we have to follow the same configuration order from H2 to N2, that is 2 to 14 electrons principle, so with the energy level order, and after of oxygen to neon order with above 14 electrons, that is we have a so called as oxygen to neon order. So we will take CO molecule into consideration, but what is the main important aspect is we have to draw this diagram based on the very important aspect that we should not draw these atomic orbitals with the same energy. We should draw the diagram with atomic orbitals with somewhat a small variation in the energy levels. So that's why one is going to be in the somewhat small energy higher than the other. So this is represented in our diagram, it is reflected in our diagram, so that it should be there. So you should note that point. And previously in the case of homonuclear diatomic molecules, both atomic orbitals, you take 1s and 1s, 2s 2s, 2p 2p, both are on the same plane or same horizontal line. But you take this CO, so 2s is somewhat of carbon is somewhat higher in energy, higher in representation of energy, and 2s of oxygen is somewhat lower in its energy. Okay, and you can see it in the picture as clear that. Okay, now let us go on to the, let us have the molecular orbital configuration of CO, and you see it is having the isoelectronic configuration with nitrogen, because the total number of electrons again is equals to 14 electrons. Therefore carbon is with atomic number 6 with electrons number is also 6, and oxygen is with number of electrons is equals to 8 with atomic number 8, and therefore 6 plus 8 is equals to 14 electrons, and it has isoelectronic configuration with nitrogen molecule. So its configuration order is going to be sigma 1s 2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p x2 is equal to pi 2p y2, and sigma 2p z2. So here this is the configuration for CO molecule. And you take the very important CO molecule, it is having a so-called carbon and oxygen with atomic orbitals like carbon electronic configuration is 1s2, 2s2, 2p2. Oxygen is with electronic configuration of 1s2, 2s2, 2p4. Let us now have the first 1s atomic orbital will combine with 1s atomic orbital and give stress to the formation of two new molecular orbitals, that is sigma 1s2 and sigma star 1s2 with completely filled with electrons. And you take the second shell, 2s atomic orbital of carbon combines with 2s atomic orbital of oxygen and with completely filled with electrons, gives stress to the formation of two new molecular orbitals, sigma 2s2 and sigma star 2s2, again filled with completely electrons. And you take the next higher order, next higher energy state, 2p orbital of carbon is with only 2 electrons, whereas oxygen with a 2p orbital with 4 electrons are there, and totally 6 electrons are present. So 2 plus 4, 6 electrons are present. Now distribute those electrons in the bonding molecular orbitals first, followed by anti-bonding molecular orbitals next. So therefore first we'll take, so pi 2 px is equal to pi 2 py orbitals, and we distributed 4 electrons in these, and distribution of 4 electrons is done in pi 2 px and pi 2 py. Then remaining 2 electrons are distributed in the sigma 2 pz orbital. So their configuration is going to be the, so pi 2 px2, pi 2 py2 and sigma 2 pz2. And whereas anti-bonding molecular orbitals like pi star 2 px, pi star 2 py, sigma star 2 pz orbitals are empty. And you take this important total molecule. This is the diagrammatic representation of entire molecule, and you see in the diagram carbon is having configuration, and oxygen atom is also having configuration order, and which are distributed in this way. So starting with sigma 1s2, sigma star 1s2, so with the atomic orbitals of carbon and oxygen 1s and 1s, and sigma 2s 2, sigma star 2s2 with the atomic orbitals of sigma 2s atomic orbital of carbon and 2s atomic orbital of oxygen. And 2p orbitals are combining. Here in the case of carbon, 2 electrons are present in 2p orbitals, 2px1, 2py1, and 4 electrons are present in the oxygen, 2px2, 2py1, 2pz1. And you take this order of configuration, pi 2px, pi 2px2, pi 2py2, sigma 2pz2, and the anti-bonding molecular orbitals are empty. And that is explained based on this molecular orbital diagram. And the molecular orbital configuration is represented here. The molecular orbital configuration of CO is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2, and next sigma 2pz2, next pi star 2px2, sorry, pi star 2px0, pi star 2py0, and sigma star 2pz0. This is the configuration order. And you take the bond order calculation. It is given by the formula 1 by 2 is equals to Nb minus Na, or 1 by 2 is equals to the total number of electrons that are available in bonding molecular orbitals, or we have, so we have how many number of electrons are present in bonding state. So sigma 2s, so it is equals to the nitrogen configuration, right? So same as nitrogen, there are totally how many bonds are, I mean, what is the bond order of oxygen and nitrogen we have learned in our last explanation of the molecules. So you take the nitrogen, what is its bond order? 3. So you take the bond order is equals to 3, therefore the bond order 3 represents even in the case of CO molecule also there is a triple bond that is present. So therefore the triple bond is representing, it is represented as like this. The bond order of CO is represented with 3, so it is representing with the so-called a double bond, I mean a sigma bond, 1 sigma bond, and 2 pi bonds are present, and its bond length is going to be 1.112 angstrom units. And you see it exhibits what type of magnetic property? It exhibits again a diamagnetic property, because all molecular orbitals are with pair of electrons. You see, this is the case of CO molecule, and we have one more molecule that is called CO molecule, which is represented with positive cation on the top, that is CO plus molecule is also there. If we want, we can have that one also. CO plus is with totally we have 13 electrons are present. If we distribute those electrons, then we will get a total of its bond order, and it is going to be taken as like the CO plus. So total electrons are 13. So therefore sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, and sigma 2pz1 is going to be there. Therefore totally we have the bonding molecular orbital electrons are we have how many? 7 are there. Anti-bonding molecular orbitals are how many? 2 are there. 7 minus 2, it is by 2. So totally it is going to be how much? 5 divided by 2, and it gives 5 by 2 is the bond order. Okay. So now we will be moving on to the next important molecule of heteronuclear diatomic molecule called NO. So NO is again a heteronuclear diatomic molecules. You take nitrogen is with an atomic number of 7 with electronic configuration of 1s2, 2s2, 2p3, and on the other side oxygen is with a atomic number of 8 and its electronic configuration is 1s2, 2s2, 2p4, and the total of we have nitrogen plus oxygen 7 plus 8 is equals to 15 electrons are present. So above 14 will follow the configuration of oxygen to neon order. So therefore the energy level increasing order is going to be sigma 1s, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi 2p x2, pi 2p y2, and remaining one electron will go and occupy either in we have the pi star 2p x1 or else pi star 2p y1. So this is the configuration order of NO molecule, and you take this is the energy level diagram. If you look at this molecule carefully, so we have first 1s atomic orbitals. So 1s atomic orbitals like sigma 1s, sigma star 1s are completely filled with electrons because actually sigma 1s and sigma star 1s are the bonding and anti-bonding molecular orbitals that are formed from atomic orbitals called 1s atomic orbital of nitrogen and 1s atomic orbital of oxygen. Okay, so next because of this combining of 1s atomic orbitals of nitrogen and oxygen, there will be formation of molecular orbitals of sigma 1s and sigma star 1s with a pair of electrons, and next we will be moving on to the 2s and 2p orbitals. In the case of 2s and 2p orbitals, nitrogen atomic orbital 2s combining with oxygen atomic orbital 2s and gives rise to sigma 2s and sigma star 2s with a completely filled with electrons, that is sigma 2s2 and sigma star 2s2. And the next one is 2p orbital. Nitrogen is with 3 electrons, and whereas you see that is px 2px1, 2py1, 2pz1, and oxygen is with 2p orbitals, or 2p with 4 electrons, that is 2px2, 2py1, 2pz1. While these orbitals combine, there will be formation of sigma 2pz with the lowest energy, and the next pi 2px, pi 2py degenerate orbitals with the next higher energy, and the next pi star 2px, pi star 2py, and the highest energy is going to be the sigma star 2pz. So distribute those totally we have 4 plus 3, 7 electrons are present. First sigma 2pz with the 2 electrons, next pi 2px, pi 2py degenerate orbitals with 2 electrons, that means totally 4 plus 2, 6 electrons are distributed in the bonding molecular orbital state, and the remaining 1 electron will go to the higher energy, that is anti-bonding molecular orbital state. Either it will go to the pi star 2px orbital or else it will go to the pi star 2py orbital. So we can't exactly specify which orbital this electron is going to be occupied. So okay, so this is the configuration order. Now if you calculate its bond order, so you take the bond order formula, that is number of bonding molecular orbital electrons minus number of anti-bonding molecular orbital electrons divided by 2. So for this to calculate, first we should understand about how many number of bonding molecular orbitals are present and how many anti-bonding molecular orbitals are present with electrons. And let us go for this. First, non-bonding orbitals are sigma 1s and sigma star 1s, which are not participating in bonding, which are called inner orbitals. So you take the sigma 2s, sigma 2pz, pi 2px and pi 2py are the 4 important bonding molecular orbitals with pair of electrons, and hence a total of 8 electrons are present in bonding molecular orbital state. And you take the next one, that is anti-bonding molecular orbitals, sigma star 2s, pi star 2px or pi star 2py. So there are a total of three electrons that are present. That means sigma star 2s is with a pair of electrons and pi star 2px is with only single electron. Therefore a total of 3 electrons are present in antibonding